Hi guys. So I'm going to talk about balancing chemical equations today. So when we balance chemical equations, what we're actually doing is we're making sure that the law of conservation of mass is upheld. So the law of conservation of mass states that matter cannot be created and it cannot be destroyed. So when we do chemical reactions, everything that we start with on the reactant side has to be present in the product side, meaning that all of our atoms have to be accounted for so that we don't lose any and we don't just create any out of thin air, because that just doesn't happen. So when we have a reaction like this synthesis reaction where I've got magnesium reacting with oxygen to produce magnesium oxide, in order to balance it, I want to make sure that I have the same number of magnesium atoms on the reactant side as I do on the product side. And similarly, I want to make sure that I have the exact same number of oxygen atoms on the reactant side as I do on the product side. So I'm going to show you the mathematical way that I can do this for this reaction. So because I am looking at reactants versus products, what I do first is I actually draw a line directly under the arrow, because that separates out visually the reactant side from the product side. And then I make a list of everything that I have. So on the reactant side, I have magnesium and I have oxygen. And that is also true on the product side. I have magnesium and I have oxygen. Now I want to know exactly how many atoms of each of these elements that I have. So on the reactant side, I have one magnesium atom. And I know that because I don't have a subscript written down next to magnesium. And if I don't have a subscript written, then it is the implied subscript of 1. So I have one magnesium atom on my reactant side. For oxygen, I have a subscript of 2, which tells me that I have 2 oxygen atoms on my reactant side. Now on this side, my product side, I have 1 magnesium atom and I have 1 oxygen atom. So immediately I can see that my magnesiums are all accounted for. I have 1 magnesium on the reactant side and I have 1 magnesium on the product side. But I do have a problem in my oxygens. I have 2 oxygens present on the reactant side and only one of them is accounted for on the product side, and that can't happen, so I need to fix that. So we use multiplication when we are balancing equations. So the question I ask myself is, what can I multiply this 1 by in order to equal 2? Well, clearly the answer is 2, because 1 times 2 gives me 2. But this is a compound, magnesium oxide, and I can't do something to only half of this compound. So since I had to multiply the oxygen by 2 in order to even them out, and this oxygen is attached to this magnesium, I also have to multiply the magnesium by 2 as well. It's like in math class when you distribute. Okay? If I do something to one part of the factor, I have to do it to the whole thing. So because they are connected in the compound, what I do to the oxygen, I must do to the magnesium. So I have to multiply that magnesium by 2 as well. Okay? So then when I do that, you can see that I have now balanced out the oxygens. I have 2 oxygens now present on the product side to match my 2 oxygens that I started with from the reactant side. But I've messed up my magnesiums because now I have 2 magnesiums on the product side and I need to make sure that I have 2 on the reactant side. So I'm going to multiply my reactant magnesium by 2. Now on the reactant side, you can see that magnesium and oxygen are separate substances, and so therefore I don't have to do anything with the oxygen on the reactant side because it is not attached to that magnesium. So I can do that and be done because they aren't in the compound together on this side. So if I take a look, now I've got 2 magnesiums for my 2 magnesium, so they are balanced. And I have my 2 oxygens for my 2 oxygens, which means they are balanced. So now I have balanced it, and the very last step is to put coefficients. Now the coefficients are the multipliers, right? So the things that I have multiplied by now become my coefficients. So when I rewrite this, if I rewrite this, it's going to be magnesium plus oxygen is going to be magnesium oxide. But now I'm going to add my coefficient. So I multiplied my magnesium by 2, which means that I'm going to put a coefficient of 2 in front of my magnesium. So this multiplier becomes my coefficient. Okay. And over here on my product side, I also multiplied this by 2. So just like what we did before, we're going to take that multiplier, that 2, and we're going to put it in front of the magnesium oxide, okay, as the coefficient. Okay. Now this oxygen on my reactant side, I did not have to touch him, so I didn't multiply that by anything, and so I don't have a coefficient that I need to write in front of the oxygen. But just like where without a subscript written, it's implied that the subscript would be 1. If I do not write a coefficient in front of a substance, then the implied coefficient would be 1. So when I would read this out, I would say 2 magnesium react with 1 oxygen molecule to produce 2 magnesium oxides. And that would be my properly balanced equation. Now to look at another one, okay, I have copper 2 carbonate, CuCO3, decomposing into copper 2 oxide and carbon dioxide. Okay. So in this decomposition reaction, let's see if it is balanced. So I'm going to draw my line underneath, okay, to separate out my reactants from my products. And I'm going to list my elements. So I have copper, and I have carbon, and I have oxygen on my reactant side. And I have 1 copper, 1 carbon, and 3 oxygens. I'm going to do the same thing on the product side, but you can see already I've got oxygen in multiple places on my product side, which means I'm going to have to list it multiple times. So I'm going to list the oxygen that I have that's bonded to the copper, and then I'm going to list the oxygen that's bonded to the carbon. So I have 1 copper atom and 1 oxygen atom that's bonded to it. And then I have a carbon atom, and I have 2 oxygens that are bonded to that carbon atom. So now that I have oxygen in multiple places, I want to make sure that I keep a total tally. So over to the side here, I'm going to have total oxygens. And right now, I have 3, because I have these 2, and I have that 1, and 2 plus 1 gives me 3. Okay, so if I go ahead and I take a look at this, I have 1 copper on my reactant side, and I have 1 copper on my product side, so they are balanced. Okay. I have 1 carbon on my reactant side, and I have 1 carbon on my product side, so they are balanced. And I have 3 oxygens on my reactant side, and I have 3 total oxygens on my product side, so they are balanced as well, which means that this reaction is balanced already, which is a great thing for us. So now that I know that, if I wanted to rewrite it, I could. But since I didn't have to fix anything, since it was already balanced, that means that all of the coefficients in front of my substances would be ones, and I don't have to write the ones because the ones are implied when I write the formula. So for this, we would say it is already balanced, and we would leave it as it is. To look at another one in a slightly different way, there is another way that we can go about balancing equations, and it is to use some drawings. So if we do that, it follows the same pattern of we always start with separating out the reactant side from the product side by drawing that arrow, the line underneath the arrow. But if we're going to do this with drawings, then we assign some shapes to each individual element. So for example, let's call potassium squares. Chlorines can be triangles, and oxygens, we'll keep it easy, we'll keep them as circles. So we'll do the same thing on this side. So potassiums are going to be squares, and chlorines are going to be triangles, and oxygens are going to be O's. Okay. So this is one big compound, meaning that the potassium and the chlorine and the oxygens are all bonded together. So when I draw this molecule, what I want to do is make sure that I put them all together. So I have one potassium, so I'm going to draw one square. And I have one chlorine, so I'll put my triangle representing my chlorine there, and I'm going to make them so that they touch to show that they are connected. And now I have three oxygens, so I'm going to draw three circles on my big conglomeration here, also touching. Okay. So this is going to represent this, with my one potassium, my one chlorine, and my three oxygens. Okay. Now I'm going to do the same thing for my products. For my products, I have one potassium, and it is attached to one chlorine. So when I draw my square and my triangle, I'm going to have them connected because they are together. Okay. And then I also have oxygen, so I have two oxygens that are also connected. So I'm going to draw my two circles connected. So now what I have to do is I have to make sure that I have the same number of squares on both sides. So I have one square on my product side, and I have one square on my reactant side. So far things are looking good. Okay. I have one triangle on my product side, on my reactant side, and I have one triangle on my product side. So that is looking good. But I have three circles, and I only have two circles here. Okay. Now, since they're not balanced, I have to fix those. Now, if I draw another O2, okay, that will bring me to 4, but it's still not going to equal 3. So what I have to think about is what is the least common multiple between 2 and 3? Well, the answer to that is 6. So I can make it so that I have 6 circles and 6 circles. But if I do that, I can't just draw 3 more circles. I have to draw a whole nother one of these compounds because it's all connected together. It's one big thing. So if I need to get something more, I have to draw the whole thing again. So I'm going to go ahead and do that. Okay. And so now I have my 6 circles on my reactant side. So I'm going to get to 6 circles over here by drawing 2 more of my O2 representations. Okay. So now I have 6 circles on my product side, and I have 6 circles on my reactant side. So now my circles, which represent my oxygens, are balanced. But what I've done is I've messed up my squares and my triangles that represent my potassium and my chlorine. So now I have 2 squares on my reactant side versus 1 square over here. But if I draw another one of these compounds, now I have 2 squares, 2 squares. So we're good. And I have 2 triangles, and I have 2 triangles, so we're good there as well. So now everything is balanced, so now I just need to get my coefficients. For those, in this method, you look at how many of the drawings did you do. So here I had to have 2 of these drawings, which means that I'm going to have a coefficient of 2 in front of KClO3. Okay. And I also have 2 of these drawings, so my coefficient in front of KCl is also going to be 2. And I had 3 of these, so my coefficient in front of O2 is going to be 3. So the properly balanced equation then would be 2 KClO3s decomposing into 2 KCl's and 3 O2s. And that would be my complete balance equation. So either way that you want to balance, whether you're going to do the symbols or whether you're going to do the mathematical version with the multiplication, will get you to the same answer. So it is up to you which one you prefer. But in either method, you're always trying to get so that your number of atoms of each element on the reactant side is equal to the atoms of that element on the product side. And you're not done until that is true for every element, reactant side and product side. And that is balancing equations.